we've introduced the idea of what an antiderivative is, and we've worked out quite a few examples using the reference rules on our new bestest friend derivative and antiderivative rule sheet. You may notice as you look through there, though, that there are some derivative rules that didn't seem to have a corresponding antiderivative rule. In particular, you may notice the product rule is missing. So is the quotient rule, and we end up using those quite often. You might be wondering, well, is that something that we're going to end up getting a Mark III version of the sheet later? Not really. So I want to take a look at some examples where you might think you need a product rule or a quotient rule and point out how you can get around it. So for starters, what if we had something like this? So we have 2x plus 1. Actually, I want to change this. Again, I like to keep you on your toes using different variables, so I want to change that to a z. So now we're looking for an indefinite integral with respect to the variable z. Okay, so we have 2z plus 1 times z minus 3. Your first move might be, well, maybe I can just find an antiderivative for this, find an antiderivative for this, then multiply them together. You can go ask Steve Harvey. Survey says, bah, it's not going to work. So we got to do something else instead. I've mentioned there's technically an analog of the product rule. We don't cover it in Calculus 1. If you want to know what it looks like, stick around for Calc 2. Otherwise, we need to do a little algebra before we can actually come up with an antiderivative for this beast. So, our old friend, the FOIL algorithm, comes back again. First, 2z times z gives me 2z squared. Outer 2z times negative 3 would be minus 6z plus the inner 1 times z. So we have negative 6z plus 1z. Still trying to write x's. Did you catch that? So negative 2z squared minus 5z. All that's left is the last. 1 times negative 3 minus 3 dz. Now we can use the power rule like we did on that previous polynomial example, working our way through coming up with an antiderivative for each of these guys. So an antiderivative of z squared, here was our first example. 1/3 z cubed, I'm going ahead and multiplying that guy by 2, minus 5/2 z squared. And if you're not careful at this point, you'll do what I'm about to do. You'll write 3x, you'll write plus c, you'll call it a day, and then I'll come back later and say, how did you end up with 2 variables all of a sudden? Oops. Yeah, you should only have 1 variable in your final answer at this stage. Phi x. That was a z. It's always been a z. We have always been at war with East Asia. Okay. If you don't get that reference, don't tell me. It'll make me feel old. So anyway. So there's our antiderivative in this case. So we don't need a product rule for any examples that are going to come up at you in this course. Technically, yeah, you might end up, if you're feeling particularly inquisitive, saying, well, what happens if I can't FOIL this out? What if it's like, z squared times cosine of z, or e to the z, or something like that? That's an excellent question, and if you take Calculus 2, you will have your answer. For now, we're just going to let it ride like this. All right? All right. So I've got one more example I want to take a look at, and you might be able to guess where this is going. So we talked about products. The same thing is applicable if we're dealing with a quotient. So I've got x to the 5th plus x plus 1 divided by x squared, and I want an indefinite integral for that guy. There's not really an analog of the quotient rule that works, so, let's put it this way. I've been at this for 2 decades now, and I've never seen an antiderivative quotient rule. There may be one, but I've gotten by quite happily without ever needing to come up with one. Instead, like with the FOIL thing from our product example, we can break this thing up and then resolve what's going on. So what I'm going to do is break this thing up into 3 separate fractions. This over x squared, this over x squared, this over x squared. So So I've got three separate fractions. And now I can use my properties of exponents to chop this thing down into power functions that I can find antiderivatives for. So again, still no calculus yet. This is algebra. So x to the fifth divided by x squared, I've got x cubed. X divided by x squared is x to the minus first. This guy will just give me x to the minus second. Again, don't try doing like a quotient rule thing or anything with that over. And please don't tell me that it's just 1 over 1/3 x cubed. That is, you can check really quickly. That doesn't cut it. So now, however, I can use my bestest friend reference rules in order to come up with antiderivatives. This guy, I use the power rule. 1/4 x to the fourth. X to the minus first, that's the one where the power rule doesn't work, but we've already said his antiderivative is ln of, that's right, absolute value of x. And then lastly, adding 1 to my -2 gives me a new exponent of -1. Dividing by -1 is just going to change the sign here. So there's an antiderivative. If you wanted to untangle this and write it as -1 over x, that's fine. I get why you'd want to do that. I'm okay with negative exponents, though, for what it's worth. So that's how to handle products, how to handle quotients. There's technically another way you might try to resolve this. I don't recommend it, but a lot of students end up going this route. So, because fractions are scary, I get that. What a lot of students will end up doing is reinterpret this thing like so. So they pull the x squared up top as an x to the -2nd, and they say now it's a product, I can distribute that x to the -2nd. If you do that, that's perfectly fine, and you'll end up back here. The problem I see students run into is that making that particular move, it seems to cause all kinds of algebraic problems. I've seen way fewer students mess this up than try to do this, but then they'll just like write plus x to the -2nd, and so now they have 4 terms, or they'll write it as a minus because they remember something about changing signs, so they put a subtraction at the end. It just feels like going this route gives you more chances to slip. If you're comfortable and you're confident enough in your algebra skills to go this way, have at it. I'm perfectly fine with that. But it feels like the safer road, even though it may look a little scarier because of the fractions, is to split things up like this. So that's the product rule, that's the quotient rule, well, how to handle products and how to handle quotients. Like I said, we don't really have those rules sitting around, but that gives you the idea. So, got one more video I want to take a look at, because if you're outside of a math class, you might not really be satisfied with these indefinite integrals, these general antiderivatives. If you're trying to model how something you fired out of a cannon is traveling, you don't really want to come back with an answer that's got this undefined constant hovering around in it. You want one specific function that's describing where the thing is flying, because you don't want to be wherever that thing lands. So what we're going to take a look at next time is how to handle that particular situation.